Chapter 7 is on the normal distribution. But before we can even talk about normal distributions, we have to talk about probability density curves. So a probability density curve is a curve where the entire area underneath it is equal to 1. But sometimes it doesn't have endpoints. And that's what will happen with normal distribution here in a minute. But we need to understand that that the entire area underneath it is 1. So 100% of the area is under 1. And I'm going to kind of use the one your book goes over. And it looks like this. I mean, it can have digits. It doesn't matter. Let's say it has like something like this. This would be like a probability density curve might look something like this. And what that means is all the area underneath this is equal to 1. Okay. The area underneath it is equal to 1. Now, we might know the area between digits, like if this was 0, 1, 2, 3, 4, 5, 6, and so on. We might know the area between two of these units. We might not. It doesn't matter. With the normal curve, we will know that, which is nice. But I need you to start kind of understanding, hey, when you see this curve, the entire population is underneath the curve, okay? So is an example where it tells you the area between two of these units. So like, let's say this was 0.16, that the area between it. So the area between this is 0.16. What that means is the population, I should say the proportion of our population between 3 and 4 is 0.16. So 16%, right? 16% of our population, we can use kind of a different color just to look at it. So 16% of our population is between 3 and 4, okay? 16% of our population is between 3 and 4. Now, what that also means is that what, like 84, the proportion that is not between 3 and 4 is 0.84, right? So the proportion of the population that is not between there. So if we use like a totally different color, let's use like this red kind of color, right? If you're in the red here, this means you're not between 3 and 4, right? That population, that red population there, would be 0.84, 84%. So 84% would lie in the red, where 0.16 would lie in the blue there, okay? Now, let's say we knew that the proportion less than, excuse me. Let's say we knew the proportion less than 3. So this group right here. Let's say we knew the proportion less than 3 was, let's say, 0.45. Well, this would mean this upper, and we're going to call it a tail. This tail right here, so I'm going to shade it a little differently, just so it looks a little different. This tail here, now if 45% lies here, 16% lies here, we add those together, we get what, 61%, right? So that means 0.39 has to lie there, okay? So notice all of these add up to 1 because this is all the areas under this curve. We've kind of broken it up into 3 different areas. Typically, we'll break it up into 2 areas. You'll see as we go along. But, yeah, I think that's the best way to say it. It's just an introduction. When your brain sees a curve now, I need you to think, hey, there's 100% of our population under that curve. And we're really trying to see where it divides it out, okay? What's below and what's above, what area is below and above. And the area.
Okay, so how would you figure that out?
Yeah,
how do you know 3 and 4 is 0.16?
We'll get there. We're not there yet. This is the introduction to the visual part. I'll get to the algebraic stuff here in a minute.
Sure.
And
10th
And our
grade,
calculator,
yeah, right.
which is nice, Lori. Our calculator will do a lot. Because I'm not even going to show you how to do it by hand. You have to use a chart. Well, let's talk about that. But before we use a chart, actually, we can use a standard rule, and it's on the next page. So this is 396. I'm kind of following along in the book here if you want to follow along. Your book then starts to talk about the normal distribution and the normal curve. And I'm just to make sure I'm on the same page because sometimes books describe things differently. But it says the probability density curves come in many varieties, depending on the characteristic of the population they represent. Remarkably, many important statistical procedures can be carried out using only one type of probability density curve, which is called the normal curve. A population that is represented by a normal curve is said to be normally distributed or have a normal distribution. Figure 7.4 represents some examples of normal curves, right? Yeah. So a normal curve is just, that nice bell-shaped curve, right? I mean, a nice bell-shaped, and you could draw a few different ones if you want. Like, I'm going to go over what they're kind of talking about here. I'll use different colors. 1, 2, 3, 6. -1 here. So if we wanted one that lined up like at 0, that's a nice curve there. Now you need to understand that these really go forever to the right and forever to the left. Theoretically, now I need you to understand this theoretically. Theoretically, they're going to get closer and closer to 0, but they're never going to get there. It is called an asymptote. If you remember that in
Asymptote, yeah.
Remember that in college algebra? That is
That's a weird word.
It is a weird word. Asymptote. But now look, notice this. If we just wanted to describe this normal distribution, it's mean. Okay, look, the middle here is going to be the mean and the median. So this curve is going to have a mean of 0 because the middle's 0. Now, I don't know the standard deviation. I'm going to make this up just to show you what's going on. Let's say this has a standard deviation of 1, okay? And it's for reference on the next one, okay? Standard deviation of 1. So let's say we find another population. I'll use this red color. And now remember, 100% of our population lies under this curve, right? So this one, we've got this other population. It doesn't relate at all to this blue one. Now we've got this red one. And it looks a little different. It looks like this. Okay. Now again, the middle though is at 3 here. So this distribution has a mean of 3. But look, notice how much steeper it is. Because it's steeper, the standard deviation is going to be, hold on. Because it's steeper, the standard deviation actually is going to be smaller, okay? The standard deviation is going to be smaller. So let's say this standard deviation winds up being like 0.25, okay? 0.25. So steeper standard deviation means smaller standard, steeper curve. I should say it that way. Steeper curve, smaller standard deviation. So let's do one more with a flatter curve. Let's say.
What's the symbol for standard deviation?
Standard deviation is sigma. It's a lowercase sigma. Kind of looks. I think in text it looks like that. Oh, you know what? Hold on. Let me spotlight this because people at home are going to see whoever's talking. So it looks like this, but when I write it, it winds up looking more like that. But they're all the same here. Okay.
Oh, okay.
So it looks like
the one that you have in the red.
Yeah.
It just doesn't look like that. That's why I was asking.
Right. And I'll tell you,
okay,
it's like on a computer text, it looks more like this. But the way math people typically write it, it's like that. And I don't know why.
Almost like a T with a line.
A line here, yeah.
Yeah, okay.
Okay, now let's look at no problem. Let's look at a more flat standard deviation now, and let's center it at like 5. So if we had a flatter curve, it's still considered normal. But let's say we had a flatter curve here. Now this one's centered at 5, so the mu would be 5, but we've got a flatter curve, so that means the standard deviation is going to be larger. So we'll say this one's 2. Why not? I don't exactly know. I'm just kind of giving you examples. So a flatter curve, larger standard deviation, and a more steep curve is going to have a lower standard deviation. Really what that's saying is the amount of data, the same amount of data or the population. Well, we'll get there. I'll talk more about that in a second. Okay. Now I'm going to just read these properties of the standard deviation. So, or the normal distribution, I should say. It's on page 297. It says, 1, normal distributions have one mode. Like if you look at this, there's one mode. It doesn't peak twice. That's what that's saying. 2, normal distributions are symmetric around this mode. So the mode is always in the middle, okay? And the mean and median are always in the middle too, okay? But we're symmetric and the mode is in the middle. So that's why it has that bell shape, okay? That's why they have that bell shape. 3, the mean and median of a normal distribution are both equal to the mode. In other words, the mean, median, and mode of a normal distribution are all the same. So like I'm going to focus on this blue one right here. I don't know if it's blue on your screen, but this first one. The mean, median, and mode are all 0, okay? That's what's really neat about this normal distribution is the mean, the mean, so the average, the median, the middle, right? So what the median means is if this is the median, look, 50% of our data lie to the left and 50% of our data lies to the right because it's the median. Remember, median's in the middle. And then the mode means the most amount of our data lines up in the middle. So that's what makes the hump in the middle, okay? That's what makes the hump. And then the mean aspect is the fact it's weighted the same on both sides. It's not like, it goes weird and then swoops down. Since it's symmetrical, it's going to have the mean in the middle, okay? Mm-hmm. And the last thing your book goes over on this is the normal or the empirical rule. And I thought we went over it already, but I'm going to go over it like I haven't because I don't know why I would have gone over it with you guys already in this class. So this is called the empirical rule. Sometimes it's called empirical approximation. It depends on which book you're using. I'm going to call it the empirical rule. And now this is
we had only one little section that mentioned it.
Mention it. Okay. Well,
yeah.
The empirical rule was something a little different. It didn't really relate to the normal distribution. But I'll tell you, this is an approximation. It is not perfect. But Lori, remember when you asked me, hey, how do I know the percent between things? Mm-hmm. This is the first approximation into that, okay? So I'm going to draw a really big normal distribution. This is not a perfect normal distribution, but we're going to imagine this is a perfect normal distribution. And we know that normal distributions are centered on their mean, okay? Oh, it's really bothering me how horribly drawn this is, but that's okay. I'll let it go.
That's okay. I can't draw perfect either.
Yeah. Okay, what the empirical rule says is if we have a normal distribution, so we have to have one, it turns out there's 3 rules that are going to be here. But the first one is 68%, so 0.68 our population lies within 1 standard deviation of the mean. So think about this mean here. If we go up 1 standard deviation, it would be the mean plus 1 standard deviation, right? And if we go down 1 standard deviation, it would be the mean minus 1 standard deviation. We'll do this with real numbers here in a minute, okay? But the empirical rule, the first rule says, look, it turns out 68 approximately, it's not perfect, approximately 68% of our data lie, or population, 68% of our population lies within 1 standard deviation of our data. Okay. What that means, though, because there's symmetry with normal distributions, there's always symmetry. If 68% lies in between, that means 32% has to lie in both tails. So that means 16% is here and 16% is here. Okay? Right? Because it's got to add up to 100%. So
Right.
60 plus 68 plus 16 would be 100%. So I'm going to give you an example, a real world example here, that I know roughly is true. Okay. It turns out people that take the ACT, the math ACT. If I look at the math ACT, the average of the population, we're talking about populations here, not samples. Okay. The population mean for the math ACT is 21.2. Actually, I think that might be a little high, but it's about 21.2 with a standard deviation of 1.6. I think that's actually kind of, nope, I lied, guys. It's 2.6. It's 2.6. It's 2.6. It might be a little off. Let's imagine this is true. Okay. So, because we know this, we can actually find our first like approximate interval. So let's use real, I'm going to actually draw this out. Here's what we know. We know the math ACT because so many people take it, I promise, because so many people take the ACT in the math section, it winds up being a nice normal distribution. Okay. It winds up being a nice normal distribution. Now we know the mean's 21.2. Right there, right?
Mm-hmm.
Now the book's going to ask you, well, what percent lies between two numbers? And I'm just going to draw it out. I love drawing. Okay. So if I go up one standard deviation, we're going to go up one and up two. I'm going to take my calculator out and I'm going to say 21.2 plus 2.6, right? So one standard deviation up is 23.8, okay? One standard deviation down, so that's 21.2 minus 2.6. That's 18.6, okay? And what this empirical rule says is 68% of students will approximately make between an 18.6 and a 23.8 on the math ACT. I'm going to write that down. So what does this tell us? Approximately. Now you have to use approximate because it's not perfect. %68 of students will make between an 18.6 and 23.8 on the math ACT. Okay? Does that make sense, Lori?
Yeah.
Yeah, and so that's where this is the first way of us kind of knowing what's going on. Now, I'm going to fill in the other blanks, though, because we said earlier, if 68% is in the middle, 16% is above, and 16% is below, right? So it tells us some other stuff, and I'm just going to write it out. So approximately, so I'm going to say approximately APP period. 16% of students make above a 23.8 or below an 18.6, right? That's what that tells us. Now, the question might also ask, well, what percent make above an 18.6? So I'll kind of write that as a question. What proportion? If you use proportion, we don't write it as percentages. It would just be 0.16. But what percent make above an 18.6? Well, now look, I need you to think of this as almost like a Jell-O mold, okay? And we're going to slice it right here. So we're slicing it right here because it's asking for above 18.6. Below is 16%. So if below 16%, we need to add these two up, or we could just say 100 minus 16. So that's 84. 68 plus 16, 84%. Okay. So what percent make above? And that would be the same as what percent make below a 23.8, right?
Uh-huh. Okay.
Okay. Do you have any questions, Lori, before I keep kind of moving on?
No, I just had to finish writing down what you had.
Oh, I got you. Okay. So
I'm
now,
slow.
no, that's fine. That's fine. So this is the first rule, is within 1 standard deviation. Well, 2 standard deviation actually is 95%. So I'm going to draw that out.
That's what we did in one of the previous chapters. It
Okay.
was 95 and 68.
Okay, cool. I thought we did. I'm not crazy. So I'm going to just kind of write this one out. So what that means, now I'm going to use the example we had. Remember, it was centered at 21.2, that math ACT.
Mm-hmm.
The mu was 21.2. The standard deviation was 2.6. Well, it turns out if you go up 2 standard deviations, now I'm going to use my calculator again, and say 21.2 plus 2 times 2.6. So 26.4. Now, and then I'm going to go down 2 standard deviations. So 21.2 minus 2 times 2.6. So it's actually an even number, 16. So if we go up 2 standard deviations and down 2 standard deviations, this area between these two is 95% of our data. 95% of our population, I'm going to write that down. 95% of our population is between, I'm going to write it as the rule, and then I'll use the actual numbers, is between 2 standard deviations. Of the mean. So for us, that's 16 and 26.4. Okay. Now think about this though. If 95% is between these two numbers here, then the tails only get 5%, but you have to split them evenly because it's symmetric. So 2.5% would be above 26.4, and 2.5% is below 16. Okay.
Okay, now what was the formula on doing that? To get the percent? It was 21.2% times.
No. 21.2. If I want to go to here, plus 2 times 2.6, right? That's going to give me the upper boundary.
Okay.
And then if you want the lower boundary, you subtract.
21. Stupid birds. We have birds that fly into our sliding glass door.
Oh, nice. I'm
Stupid
sure the
birds.
dogs love that.
Yeah, as you can tell.
Yeah.
Jasmine. Of
Okay.
course, she barks at everything.
Yes. Now, the last one your book goes over, which a lot of books don't go over, is the 3rd standard deviation. And I'm going to just write it underneath here, because 3 standard deviations is way out. Okay. I'm going to make this a little wider. 3 standard deviations out. So 1, 2, 3. Now, again, I'm going to do the same thing, but instead of 2, I'm going to do a 3 here. So 21.2 plus 3 times 2.6. So that's 29. And then subtract 3 standard deviations. 13.4. So 3 standard deviations, your book says holds approximately 99.7. That's like almost everybody, right? Almost everybody makes between a 13.4 and a 29. Now, what that means, it only leaves 0.3% for the tails. 0.3 divided by 2 would be 0.15 in the upper and 0.15 in the lower. I'm not going to ask questions about that, but I'll tell you your book might. So just realize this is where it's coming from, okay? And it encompasses almost every single person in the population. Almost every single person in the population is between a 13.4 and a 29. Okay? Okay. Questions about that one, Lori? I know you're writing down, but do you have any questions as you're writing?
I think I got it. I think. 15%.
So now let's get to the actual areas. Remember, this empirical rule that we went over the last 2 pages, that's approximations. It's approximately true. If we want a more precise measurement, we have to use the standard normal curve. So let's talk a little bit about the standard normal curve. And that's what's in your, actually, it's not what's in your calculator. You can use other stuff in your calculator, but standard normal curve. Now, a standard normal curve always has a mean of 0 and a standard deviation of 1. That is the standard normal curve. Okay? That is the standard normal curve. And what's nice about the standard normal curve is that before we had calculators, you could use a chart to find all the areas involved with standard normal curves. So we're going to use a calculator to do it, and we can even do it if it was different means and standard deviations, but I'm going to show you how to do this with a calculator. If you are just really intrigued by this, you're more than happy to try to grasp the concepts of finding standard normal curve areas on a with a chart. I'm not going over it. I don't have time for that. So let's talk about this. Let's say you were given a standard normal curve. So that means we're centered at 0, right? And we have standard deviations of 1. -1, -2, -3. And let's say we're going to make a slice here. We're going to slice it at 0.75. Why not? Right there. And that's, these are x values. Typically, we use these as x values. So x equals 0.75. And you're like, I wonder what the area above 0.75 is. Okay? Now, we can write this as the probability above 0.75. There's nothing wrong with that. 2 different ways to write it. Now, I know this is slanted on your page because I wrote it sideways. It shouldn't be a sideways slant. It should be straight up. Yeah, that's that. I apologize for that. But that's supposed to be straight up and down. So let's bust open the calculator. And let's talk about this thing for a minute. If you go into, let's clear all this out. If you go back into the distributions, remember the binomial and Poisson?
The bars.
Yep, second bars.
Second bars.
You'll see the very first 2 options are normal PDF and normal CDF. Now, we are using CDF because we're trying to find an accumulated area. We want to find all of this area here, right? We want to find all of that area. And to find all that area, we're going to have to do the normal CDF. And it's going to ask you for the lower and upper boundaries. Now I'm going to clear mine out because that was a previous example. So now think about this. If we have boundaries here, the lower boundary would be the 0.75. Oh, not 2. 0.75, right? That would be my lower boundary for this example. Now my upper boundary is really infinity, okay? It's really infinity. We can't use infinity. Well, there's no button for infinity because it's not a real number. So we're going to have to put a really, really big number in. And I believe when you goes over this, it tells you to use like just a big, hold on. Yeah, 1E99 for the right. So what that means is 1 times 10 to the 99. So you do 1, and then, oh, there it is, the second E99. So if you look at the comma button, if you do second comma right there, whoop, second, and then comma, you'll see that means 1 times 10 to the 99. That's just really close to infinity for us, okay? So 1 and then second comma gives you the E. That means 1 times 10 to the 99. Now notice it already has the mu is 0 and the standard deviation is 1. So we want that because we're dealing with standard normal curves.
Mine just comes up E under upper.
It's just E. Check it out. It's just E.
Yeah.
Is it a capital E like that?
Yeah, that's all it is an E. It doesn't have a number after it.
No, you need to put 99.
Okay. E.
0 and 1 is the standard deviation and the mean.
So 1E99.
Yes, 1E99.
I'll get it. Okay. 1E99.
That means 1 times 10. Look, 1E99 in calculator, that means 1 times 10 to the 99th power. It's close enough to infinity for us. Okay, positive infinity. Now I'm going to hit paste. And what it does is it writes the code for you.
Okay.
And then you hit enter. Now, there's our answer. That's the proportion of the area between 0.75 and positive infinity. Now, let's round it to, I don't know, 3 decimal places. I'm not sure what the book asks, but when you get there, just do whatever the book asks. Actually, they use 2 decimal places. Let's do 2 decimal places then, because that's what the book's asking for. So 0.23. So the area above 0.75 in a normal curve is 0.23. Now what's nice is you can subtract to do the area below. So again, this would be px less than 0.75. Well, it would just, if 0.2, remember this is all 1, right? So if this is 0.23, then this would have to be 0.67, right? Is that right?
73
would be
or 77.
Yeah.
77.
0.77. My brain overthought that one.
You saw the 3 and
yeah. 0.77. So the area below 0.77, the area below 0.75 would be 0.77. Okay. So 77% of our data lies below 0.75 and on a normal standard normal curve, and 0.23 above. I'm going to see how this asks in the homework, Lori, to kind of go through some examples in the homework. Okay. Okay, hold on. Okay, that's kind of neat. So I'm going to steal some of these from the homework. Are you still writing this down?
No, I got it.
Okay. This is number 22 in your book on page, really starts on page 306 and it goes to 307. So number 22.
20.
And it gives you different areas and it's asking you to find each of the shaded areas under the standard normal curve. We did one above. Okay, let's do one between two numbers. This is part C.
Oh, there it is.
Part C, we've got, this is negative 0.5A and negative 2.48. And it's asking us for the shaded region between those two numbers. Now look, there's areas to the left and to the right, but it wants the sandwich in between, okay? It's the good stuff. Now to do this, I'm going to go back to my handy dandy calculator. And I'm going to go second varse again. I get CDF because we're adding up all the area between these two curves, or between the two lines, I should say. Now my lower boundary though now is negative 2.48. And my upper boundary is negative 0.58. Okay? So, lower is going to be to the left and upper is going to be to the right.
Okay.
And then I'm just going to hit enter. Again, our mean and our standard deviation are still 0 and 1. So I'm going to paste that, pop it in, and I get 0.227.
27.
Yeah, 0.2744. They use four decimal places.
Okay.
So 0.2744. Now, what that also, okay, so here's some neat stuff about this. I'm going to go a little above and beyond here. We'll say part C, part 2. C, part 2. What this also means is if we symmetrically went across, now remember the middle is about like right here, right? If we folded this page on the middle of this normal distribution, we would go from 0.58 to 2.48, right? That area is going to be the exact same. The symmetrically around the mean, that area is going to be the exact same. Now our mean is right here, right? 0, 0's here. Kind of neat because of symmetry, okay? It doesn't look symmetric. Hold on. Let me do it up here. It'll make more sense up here. See this blue gap?
Looks black to me.
They see this gap? Now, if this was from positive 0.58 and this was positive 2.48, it'll have the same area, okay? That'll have the same area. That's what I'm trying to say. Kind of cool. And let me steal another one just to see how they're asking these questions. Okay, yeah. So let's say we had.
Okay, I missed something. Can you go back to that paper again, please?
What's up?
Okay, so on that, you would put in there second bars CD. You would put, what would you put in the calculator if you did it opposite?
Oh, yeah, okay, so let's do it opposite to show that it's the same. So second bars, CDF. Now, the left, though, is going to be a positive 0.58 now, right?
Right.
And then to the right, it's going to be 2.48. Same thing, still 0 and 1 is our mean. Boom. you get the same exact area.
Oh, okay.
Now, neat.
Yeah, I was just trying to figure out how to. I got to go back and forth.
Oh yeah, no, I understand. I'm going to steal some now. I'm going to steal like 2 different ones. And I want you to try this one without me to just make sure you're putting the right thing in the calculator. So this is number 24. We'll do part B. It says find the area under the standard normal curve to the left
24.
of Z equals, oh yeah, they're using, okay, I need to talk about this notation. Z equals 0.53. Now I was using X earlier. Now we keep Z as for the standard normal curve. So what we're actually finding is the probability that Z is less than 0.53. So if you wanted to graph it, now Z you can think of as the X I used earlier. You know, 0.53, here's 0, right? And if here's 1, 0.53 is about right there. And they want the area to the left of 0.53. And I need to do one of these examples in the calculator. So if I'm going to use a calculator for this, I would go to second vars, normal CDF. But now look, to the left, we're going to use negative infinity. So to do negative infinity, you're going to do negative 1 E99. Okay? So negative 1 E99.
99. Okay.
But then now the upper though is 0.53.
0.53.
Still 0 and 1. We'll get to when that changes next lecture. Boom, 0.7.
0.7019.
Yep. 0.7019. So now I'm going to ask you 26. Let's do part A.
26.
Find area to the right of Z equals 0.47. So try that one, Lori.
Okay, so to the right would be 1. One. 99. 0.3191 or 92.
Yes, that's it. 0.3192. Perfect. You're getting it. Okay.
3192.
Okay. Hold on.
Okay, so
I said I was going to go on to 7.2, but I'll probably do 7.2 and like 3 or 4 together because 7.1 is such an important section. I need you to do the homework for 7.1 first. Now, I'll tell you though, the next lecture, we're going to go through like 7.2, probably 3, maybe even 4. So next lecture is going to be quite a bit longer, but this lays the foundation for the next chapter. Okay.
okay.
I'm going to pause here.
Are we going to do all of chapter 7 up to 7.6?
We'll see. I'm not there yet. Hold on.
Well, I'm just wondering because according to your schedule, Monday is when you're going to be opening the test. We're going to be doing reviews.
Yeah, no, there's no way I get to it on Monday.
Okay.
There will be a little behind.
So
It'll
that
probably-
schedule is not right.
That
Again.
schedule's not right. Let's go with the flow here. It'll probably
Okay.
be at the earliest Wednesday, Lori.
Okay.
So for homework, though, it starts on page. I flipped off the homework. Hold on.
306 for the actual homework.
Yeah.
The
Oh, yeah, that's right.
understanding is before that.
Understandings before that. So let's start with the understanding, which starts on 296, actually. This is where number 1 starts. So 1 through. And I really do want you to do all these for a reason. So 1 through. Yep. 1 through 45 odd. And I need you to hit all these before you go on to the next lecture because it's not.
Okay.